So welcome everybody. So it's a pleasure today to have Gigliola Staffilani from MIT, and she will talk about the Schrodinger equation as inspiration of beautiful mathematics.
So
Please,
thank you
Gigliola.
very much, Camillo, and the other organizers of the seminar. I don't know if many of you know, but Camillo and I went to the same high school in Italy, and we grew up about, I don't know, 6 miles apart, Camillo? I don't know, something like that.
Yeah, 10 maybe, yeah, something like that.
Yeah, so that's really nice. Okay, so I'm gonna give a kind of a more like colloquium style talk, and also will take the opportunity to describe a few results that I obtained with collaborator recently. And I like to start with a bunch of pictures because pictures are always nice, but also because the type of problems that I work on are certainly on the theoretical side, but influence quite a lot of physical phenomena. And I will not describe all these pictures here in detail, but I just wanted to put in contrast, like you realize this one is, for example, the Perron tree, which is typical harmonic analysis picture, and then some other counting that we're going to do in a little moment, which is more from the realm of analytic number theory, but very elementary. Okay, so I guess it's recognized to be true that in the last 30 years or so, the advances that were made in the dispersive equations, it's quite important. And in fact, since this is a talk of the IAS, definitely the key person that started this sort of revolutions and the beginning of so many interesting results is due to Bourgain, no doubt, especially in the type of setting which I will consider, which is the periodic one. So clearly, and then harmonic and Fourier analysis definitely play an important role, because what we need to understand in particular is the nonlinear interactions of waves. And for that purpose, it's much better to split or separate the wave into more elementary pieces and then interact and make them interact. And of course, try not to overcount when you do this type of reconstruction. Now, the analytic number theory, it's something that I will talk about in a moment. And of course, math physics, dynamical system, probability, and I will not mention in this talk symplectic geometry, but there is a part of that as well. So in order to describe all these advances, I'm going to concentrate in particular in one equation in the group on the class of the dispersive equation, which is the Schrodinger equation. And in particular, among the various Schrodinger equations, I'm going to use the cubic one, which is apparently considered to be the, the one that comes from physics, more realistic one. And well, remember there is an I here. This is very important in order to understand the difference between two completely different phenomena as dissipation and dispersion. And then there is the lambda here, which at the beginning, I'm going to just imagine to be plus or minus 1, and plus gives us the defocusing case minus the focusing case. And then there is a nonlinearity, which here I'm going to assume to be cubic. I'm writing here the initial value problem, so I'm going to give a time 0. It doesn't have to be time 0, but at some time here I'm going to fix to be 0. I'm giving you the initial profile. And the important point for the rest of the talk is that I'm considering a situation in which X is in the torus of dimension D. But really what that means is that we are considering periodic boundary data. Now, there are two important conservation laws in any dimension, which is the mass, which is the L2 norm square, and the Hamiltonian, which is the L2 norm square of the gradient, and then the L4 norm. And the lambda appears again here. And when it's focusing, the lambda is negative. And so there is a competition between the kinetic and the potential energy. And this competition, whether the first one wins or the second one wins, describe the problem as being supercritical, subcritical, critical. But I'm not going to discuss that in particular. But it's important to have the lambda here. Now, I mentioned here just these two integrals, conservation law. But in particular, if we are in dimension 1, and I will go back to this for a little bit later, we have an integrable system, and hence there are more than just these two conservation laws. But in general, for any dimension, these are it. And when we're going to talk about well, poseness in a moment, well, what you would like to do is to claim that these solutions, this problem has solutions within the physical regime, meaning just in L2 type spaces. In particular, if you concentrate on these first two guys, and if you are in the defocusing case, then what you would like to say is that you have a solution that has finite energy and finite mass. So you don't want more than just one derivative with respect to the spatial variables. Okay, so because of that, when we look at this initial value problem, we don't want it to interpret in the classical sense, in the sense of really taking two derivatives here. So we're going to recast it as an integral equation. This is via the Duhamel. And the integral equation tells you that U is expressed in terms of nonlinear interactions of U itself plus the linear evolution. So for me, from now on, ST of U0 is the linear evolution of the Schrodinger equation. In fact, it's written down here. So it's the solution of this initial value problem, which is linear. And then there is the integral 0 to t of the Schrodinger group, again, now applied in the nonlinearity. Of course, it's an implicit integral equation and doesn't tell us anything about the existence of solution, but it really gives us a way of thinking about how to solve this initial value problem in terms of proving that there is a solution. The solution is unique and is stable with respect to the variation of the initial data, and stable with respect to time as well. So if we concentrate on the right-hand side of this integral equation, we see that if we call the right-hand side an operator phi of u, then if that operator phi of u, wherever space that operator is defined, if that phi of u has a fixed point, then that will be our solution. So the solution of my Cauchy problem or initial value problem is recast as the fixed point of an integral equation. And remember from what I said before, I would like to do this by staying within the regularity given by the conservation law, hence like around H1 and not more. Okay, so we decide that we're going to look at the solution as a fixed point, hence we need to figure out what is the Banach space in which, or the matrix space for that matter, in which this fixed point can be proved to exist. So we're going to work in terms of what we're going to do, like a contraction type of argument, but still we need a space and we need a norm. So in the well, the best way to deal with this is to understand multilinear estimates in terms of the linear solution. Why is that? Well, if we go back, we're going to look at this operator here. There is a linear part, and then there is an integral 0 to t, which should smooth out somehow. And what we want to do, at least as a first stage, is to think of this nonlinear term as being a little small perturbation of the linear one. So we believe at this stage that the interactions between the linear solution should give us, or the multilinear estimates of the linear solution should give us a good intuition of what the space for the fixed point should be. So then, and we think in these terms, we arrive at the so-called Strichartz estimates. And the first person, without doubt, that was able to prove the Strichartz estimates in the periodic case was Bourgain. So let me just write down what is the estimate that we want. So we're gonna look at the LQ estimates. So for example, a good Q in dimension 2 and the cubic nonlinearity is Q equals 4. Well, the reason being that the nonlinearity is cubic, usually you estimate by duality, so you will have 4 functions and hence the L4. Now, you want an L4 norm in space, of course, but also an L4 norm in time. If you are, sorry, here. So if you are in R2 or in RD, where there are no boundary constraints, then actually what you're able to prove are LQ in the whole real line. That's because dispersion allows for the wave to, the linear wave to decrease the amplitude to 0. So you can actually integrate. But as I will explain in a moment, in the periodic case, you don't expect that. You don't expect that the amplitude of the solution goes to 0. So you have to truncate with respect to time. So, okay, we have this LQ estimates, and we want to bound by an L2 base space norm. Why L2 base? Because we discussed already that we would like to stay within the quantities of mass and energy that we have defined before, we have looked at before. And so we're going to estimate the multilinear interaction here via the HS norm Sobolev space of the initial data. Okay, now I'm going to concentrate. So there is a family of this. I'm not going to talk about all the various Strichartz estimates. I'm going to just concentrate on dimension 2 because the dimension 2 is the first kind of interesting situation we look at, and Q equals 4. Now let's write down the solution, and we can write down the solution explicit of the linear problem. How do we do that? Well, we take a Fourier transform of the linear problem. That becomes for fixed frequency and ODE. We solve the ODE and we reconstruct via the anti-Fourier transform. So at the end of the day, it will look like this. The sum n and z2, because we are in 2 dimension, u0 n, e to the I t, and then there is this is the symbol of my Laplacian on this periodic setting. And there is this omega 1 square and 1 square, omega 2 square and 2 square. Now the omega 1 and the omega 2 are related to the period in the 2 different directions that we have here. And then we reconstruct with e to the nx. Now, for the rest of the talk, actually, it's important to agree on what we call a rational torus or what we call an irrational torus. And that depends on the ratio between the periods, or in other words, this constant here, omega 1 and omega 2, omega 1 square, omega 2 square. I put the square here just because I want to make sure that's clear that they are positive. Okay, so we're going to have 2 different kinds of tori, rational and irrational. And let's see what we can say about this Strichartz estimate. So the first of this sort of estimates, as I mentioned before, were due to Bourgain in the early 90s. And he considered actually this, I say here rational, but it's really the square torus. But rational is just as well. And he proved that the L4 norm is bounded by the initial data in H epsilon, where epsilon is strictly greater than 0. Any epsilon strictly greater than 0 will do. One interesting to remark is that actually he didn't truncate in the time 0t, but that's because, I'm going to show in a second, whenever you are in a rational torus, your linear solution is also periodic in time. And that's why you have here the circle. So why is it periodic in time? Well, let's look again at how the solution looks like. And when you are in the rational torus, you can think about omega 1, omega 2 to be natural numbers. Hence, this whole expression here are squares of natural numbers, and that tells you that you can be periodic with respect to time. If it's irrational, imagine, for example, omega 1 to be 1, omega 2 to be omega 2 squared to be square root of 2, that this is not true anymore. So that's why he has in the circle. By the way, in the case in which we are in the whole plane instead of the torus, similar estimate is true, but here you will put the whole line of time. You don't have periodicity in time. And here it's enough to put the L2 norm, just the L2 norm, the mass, if you like. And that's those theorems were proved using oscillatory integrals, a restriction of Fourier transform, and so on. Okay, now what is the main proof that Bourgain gave? Actually, it's if you read it, you see that the main ingredient is counting how many points in the lattice Z2 are solutions of this equation, where now, because we are in the rational case, omega 1 square, omega 2 square are natural numbers, and R2 square is also a natural number. So I have been told that there is a lemma called Gauss Lemma that gives you a sharp estimate of the solution of this type of Diophantine equation, if you like. And that estimates in terms of how large is this ellipse. And it's R to the epsilon. And this epsilon here is exactly the loss of derivative compared to what happens if you do not have periodic boundary condition. So in this work of Bourgain, analytic number theory, I would say more elementary analytic number theory, informs harmonic analysis type results. It took about 20 years more than 20 years actually, for the general Strichartz estimate to be proved. And in fact, if you have any torus, not just the rational torus, the estimates that we were looking for in this dimension is actually true. And you again have this loss of epsilon. This is work of Bourgain and Demeter. Now, surprisingly, in this case, analytic number 3 was not part of the proof. It is in fact, these estimates are in fact consequence of the L2d Coupling Theorem, which had been a major conjecture in harmonic analysis and is related to Fourier restriction theorem and Cascade problem. And the proof of this result was inspired also by results by Larry Guth on the polynomial method and so on. Okay, so now we have a candidate for, it's a little bit more complicated than that. We have candidates for what could be the space where—
What happens, sorry, let me ask a question again. What happens if you replace the torus by, say, a compact Riemannian manifold?
Oh yeah, very good question.
And you don't know then explicit eigenfunctions.
Exactly. So there are results of that type. And in fact, this is work by Gerard, Burke-Gerard, and Setkov, and also Zahir-Hani. And the interesting part is that, for example, the best, well, you have a sharp result on the sphere. They do that. But for example, if you take a torus and you just perturb a tiny bit, the best that it's now available is epsilon equals to 1/4 in dimension 2.
So it's connected to understanding restrictions. Probably.
Yes.
Yeah.
Yes.
Okay.
Okay. So now we move
restrictions
on.
of eigenfunctions.
Yes, correct. So now we, I want to, like, just the Strichartz estimate are not quite enough. You need the so-called improved Strichartz estimate in order to do the well-posedness estimate. You need to understand what happens when, instead of just taking the L4 norm of the linear solution, you take the L2 norm of the product of two linear solution, one of which is in very high frequency localized, the other one in very low frequency. So this is called the refined Strichartz estimate. And this is some work with some of my postdoc and grad student. And then the interesting part is that Deng, Germain, and Guth proved that if you are on the irrational torus, I mentioned before the Strichartz estimate had to be proved in a finite interval time. But if you are an irrational torus, the interval time in which they are true, it's longer than if you are in the rational one. And intuitively, this makes sense because you just imagine the wave packet hitting the boundary and being an irrational torus, there is a less chance of going back to itself in a sense. And another interesting fact that I wanted to mention is that these techniques used in order to, by Bourgain and Demeter, and then Bourgain, Demeter, and Guth, to prove the L2d decoupling, were then used in order to prove some sharp decoupling for curves, which as a consequence gives the resolution of the Vinogradov mean value theorem, which is a theorem on the counting of the solution of certain Diophantine systems. So at this point, the harmonic analysis, and by the way, as I mentioned before, the proof of that Bourgain and Demeter and Bourgain Demeter Guth use, it's purely harmonic analysis. And hence, at this moment, some of the harmonic analysis estimate that people are doing are informing the analytic number theory. And there is a nice, beautiful dialogue between the two fields in a sense. I'm going to move on, and now we know that we have a candidate for our space. I'm not going to tell you how actually you go through the details of the proof for the fixed point, but what's important to know at this point is that thanks to the Strichartz estimate now for any torus, you have local well-posedness, means existing solution, uniqueness, stability, and so on in HS. But because we lose that epsilon in the Strichartz estimate, this S has to be strictly greater than 0. And this is the local well-posedness true whether you are in the focusing or defocusing. That doesn't make a difference. But if you are looking for a global solution and you want to use energy conservation in order to go from local to global by iteration, then you have to be in the defocusing case. And at this point, using the control of the Hamiltonian, you're able to claim that if you have a smooth solution, so S greater or equal than 1, you do have a global, and you are in the defocusing case, you have a global well-posedness, hence a global solution. I just want to point out that you can actually do a little bit below 1 by using the I method, but that's not relevant for us because from this point on, I'm assuming that we are smooth in terms of initial data. And the next question that I wanted to address is, okay, now that we know how the solution exists, unique and global, what happens for long times? And I'm going to mention this a little bit later. If we didn't have a boundary condition, such as the periodic boundary condition, then we actually have a scattering, meaning that we know that as t goes to infinity, the solution becomes linear, but not in the torus. So let me introduce an important concept, which goes under the bigger umbrella of wave turbulence. And the concept that I wanted to introduce is that of transfer of energy. What do we mean with that? Well, here I'm looking at the solution of the problem that I have been working on, the cubic and LS defocusing, but on the frequency space. And what I graphed here for you, this green graph, is just the graph of the Fourier coefficients. To be fair, we are in a discrete situation, so it shouldn't be a continuous graph, should be discrete, but never mind that, this is the graph. And now my question is, what happens when I evolve this initial data, which is in my picture concentrated near the small frequency, and I let time run, time becomes large. Do I have a transfer from this low frequency into high frequency? So this is the question. Now, it's a difficult question to answer also because the problem is very rigid. One example of this rigidity is, for example, the fact that if you look at the area of the subgraph that will be integrating this function, that's nothing else than the mass thanks to Plancher L, hence that will not change. So if there is a migration to high frequencies, just the area of the subgraph has to be constant. And then there is also conservation of energy, which it's harder to explain in the graph like this, but as you can say, it's complicated, it's a rigid problem. Now, as I mentioned, this goes under the umbrella of weak turbulence, but this movement from low to high is also called forward cascade. Now, you can ask something even better. I mean, it's if there is a motion from low to high frequency, does it happen in sort of a disorganized manner, as in the first little cartoon here, or in a more regular way going down, which more wave-like transport? So these are the kind of questions that I wanted to concentrate on for the remaining of the talk. Now, one way, and this is the way I learned from Jean, in fact, Jean Bourgain, one way of deciding whether there is a movement to high frequency in time is to take the object you wanted to study, hit it with a weight that is going to be bigger if you are in high frequency, and then sum over the K. Now, if this object, which you recognize as the HS norm square, in fact, if this object grows in time, that means that there is movement to the higher case. This is the reason why people are interested in the limit as t goes to infinity. And by the way, minus infinity as well is irreversible. T goes to infinity of the HS norm, where S is, of course, greater than 1, because if it's 1, we know that we can use the Hamiltonian to have this uniformly bounded. Now, there are several approaches of this problem, of this study of this limit. I'm going to look at the PDE approach, or I'm just going to say a few things. There are a lot of results, as you can see here, quite a lot of names. There is very little computation, actually, and Pan and Rabskis, these are young guys that I'm collaborating at the moment, and I will show you a recent result that I obtained with them, but there is really not much computationally. And then there is a dynamical system approach, which I will mention in a little bit. And there is a very good school in Italy, and then a Calosci and Guardia and Berti Masper are part of the Italian school there. So this is the first approach. Then there is another approach to this problem, which is more probabilistic in a sense, and it's much more refined. So the second approach is based on actually finding unaffected dynamics for this Fourier coefficient square. So how do you do that? Well, you approximate the equation, and the question is, how do you approximate it? And then take some limits. This approach also is, I'm going to has been initiated by really important names in the field of weak turbulence, and it also implies that you have a weak nonlinearity, meaning that parameter lambda that I assume to be plus or minus 1, while in this type of approach, that lambda goes to 0 because we are looking at weak nonlinearity. And what we are looking for is the effective equation that this Fourier coefficient, or at least the expectation of this Fourier coefficient square, satisfy. That's also called the kinetic equation. I'm going to discuss that in the last part of the talk. So now let me think about approach 1, which is about the growth of Sobolev norms. And approach 2, just to remind you, is finding an equation for the expectation of the Fourier coefficient square, the size of the Fourier coefficient square. Now, a first fact that I wanted to remind everybody is that if you do have complete integrability, and this is the case of 1D cubic NLS, the KdV, the modified KdV, and so on, you will not have this movement from low to high, at least interpreted as a growth of Sobolev norms, because the Sobolev norms can be bounded by using the conservation laws at any order. So we're not going to use, for this question, we're not going to use the 1D situation.
But can you see what's going on in 1D from your point of view without using this integrability and all these other integrals?
Yes, actually you can see, you can actually compute it. You need, so you have all the, you have the algorithm that gives you all the conservation laws.
So it recovers the conservation laws? You sort of recover the I mean, imagine there were some other conservation laws in higher dimensions that you don't know about.
Yeah.
I'm just asking whether in one dimension where it's integrable and where the KdV is like a nonlinear Fourier transform, whether you recover what they know or much of what they know from your methods.
Okay. All right. So my method, which method are we talking about though?
Any one of your methods which don't know about the integrability or don't exploit it.
Okay, no, so the only other method that, okay, so I'm going to talk about in a moment how we're going to estimate the growth of this Sobolev norms or not, and that doesn't give, it's not a method that will give you an algorithm to find the conservation laws when they are. On the other hand, this other method, which I didn't explain here, well, that's the I method that I worked with Terry and Jim and so on, and Mark, and they also long time ago. Yes, they do recover the conservation law, but it's not what we use here. So the second fact that I wanted to mention, which is another situation which this movement from low to high is not happening, is what I already mentioned, which is the situation in which you do not have a boundary condition. You are free to, the wave is free to disperse in R2. We are in 2 dimension here, but you can do also in higher dimension. And that's scattering. What that means is the following precisely. If so we are in R2 now, if UTX is the solution in HS, and actually because you don't lose any derivative in the Strichartz estimate, you can assume that S is greater or equal than 0, then there exists a profile U plus in your HS, such that if the linear evolution of that profile U plus gets closer and closer to your original solution U in the HS norm. Hence, this difference tends to 0 as t goes to plus infinity. And there is also a U minus if you go to minus infinity. This is actually recent result, relatively speaking, by Dodson in 2016. And why the scattering prevents this growth to the Sobolev norm? Well, that's now simple because you can use the triangle inequality, sum and subtract this linear evolution. This guy here is small, doesn't grow. This guy here is actually equal U plus because the Schrodinger operator, it's unitary in any HS norm. And hence you have your uniform bound and there is no growth of the Sobolev norm. So you wanted to definitely avoid these 2 situations. So the situation that I was looking at the beginning, which is the cubic NLS defocusing in the periodic case, is the first kind of interesting situation to look at. And in fact, there are now results in both directions. Let me explain. So if you believe that there is a growth, you want to ask how much can it grow? So these are bounds from above. If you believe that there is a growth, you also want to exhibit something that grows. And this is more like a bound from below in a sense. So I'm going to concentrate first on the bound from above. And in fact, there is again a result originated by Bourgain based on Strichartz estimate given only in the rational torus, because that's what was known before. But then once you have a Strichartz estimate, you can do it for any torus. And some of my former students, Schrodinger, did using an upside down I method, if you like. And what you can say is no matter what is your global solution, independent of the initial data, you can prove that there is a polynomial bound, which is not more than this degree here. And this concept, of course, depends on the initial data. So the best result that is known so far is 2 times s minus 1 plus an epsilon. But in a very, very recent result with Rabsky, Pan, myself, and Wilson, we prove that if you are in the rational torus, this degree actually improves. And you have that you can uniformly bound at any solution with like t to the epsilon, where epsilon just... Yeah.
Irrational means generic irrational or every irrational? I'm a bit skeptical. I mean, actually, an irrational can look like a rational for a long, long time.
Right. So it's actually every irrational, but the constants here will change.
Wow. Okay. That's
yeah. So, and I will try to let's see if I can try to explain it. But it's yes. So as long as you have, and
so no Diophantine condition on that.
No, for this, of course, if you wanted to have, you know, you start looking at these constants and then these epsilons in a better way, depending on the initial data. I mean, actually this constant here, and then it doesn't make a difference. So now let me talk about the bounds from below, in the sense that what do we have solution that actually exhibit some kind of growth? And just we don't know that as well. And in fact, there are 2 results that I want to mention. The first that I proved with this team says the following: fix your regularity, that's not important as long as it's greater than 1, otherwise it's not interesting. Fix delta, which is very small, and fix k, which is very big. Then for the defocusing, d-cubic, NLS, but on the rational torus, you can construct an initial data U0 in HS such that if you wait long enough, but it's a very long time, although the initial data is smaller than delta, you can make the evolution as large as k. So in other words, pick a small delta, pick a large k, you can construct a solution that starts small as delta and ends as big as k. Why this is not really satisfactory in a sense, because we have no idea what happens after capital T. It might go down again. Our theorem doesn't tell much that. And it doesn't even tell you if anything grows logarithmic, in fact. And another fact 4, is also...
Sorry, Gigliola, is it just like really an epsilon delta result? So, or is it quantifiable in some way?
Well, okay, the delta is given, the k is given. What you can really quantify is how long you have to wait for, given this. Okay, let's fix S, that's not important. And we didn't do it in our work, but in a later work of Kaloshin, Guardian Kaloshin, they who are more dynamical system people, they actually have some kind of quantification of how long you had to wait. Okay, so then the second result that I want to mention is the one by Carl and Fau, which is not looking at the HS norm. They actually look at the evolution in the frequency space of the solution. They start by exciting 4 frequency in this box, and then they prove that there is an initial data that in this excitement of this frequency has to make such way that you can find something later on in time that survives for large k. Now, one thing that I want to remark is that both these results are for the rational torus. So let me just first tell you, like briefly in 2 slides, what was used to prove this first result, because it involves dynamical system. And then I'm going to mention something about the irrational torus. So the way we prove the first result, that there is this, it's really this movement from low to high although we don't know what happens after capital T. It was done by starting with the original NLS, really looking at the Fourier coefficient, expecting that if there is a growth comes from the resonance set, and then build a toy model like I wrote here that takes quite a lot of this of the structure, the resonance set into account, and also truncating in the number. So we have a finite dimension object that depends on n, and then try to claim that this toy model really captures the whole growth of the original larger equation. So whatever remains after you take this out, it's small compared to the evolution of this guy. So really that's what it comes in. And it is extremely important to look at the resonance set, and in particular inside the resonance set, construct a very special set of resonances that is finite dimension, which is linked to this capital N here. And then what you want to do is the following. This toy model actually maintains the conservation of mass, momentum, and energy. And in particular, the conservation of mass tells you that the whole dynamics happens in this sphere on the, well, we are talking about complex number here, but in this sphere in the complex Cn. And you also realize that there are certain great circles that are invariant with respect to this dynamics that we have for the toy model. So at the end of the day, what you really want to prove is that you can stay close to this first invariant circle, and somehow the dynamics avoids all the other obstacles and tells you that you can get at the end in the final great circle. And in a way, this reflects the rigidity of the problem, because you had to miss all these obstacles and you had to cook up the initial data so that this happens. But we managed to do that, and we managed to prove, to construct an initial data that does exactly what you wanted to do, which starts small and ends big in terms of frequency. And then I mentioned here Guardia and Calochen and how Procese did more work on this from the dynamical system point of view. Okay, now a little bit, couple of things.
Can you say, can you go back to what, I don't know what the dynamics are. It's a difference equation that you had up there?
Is this this is the system. You had to study this system.
What kind of system is that? Is it Hamiltonian? What is it?
No.
Nothing?
Well, it's actually conserves so it's a nearest neighborhood interaction. That's the gain that you have by using this and not the whole Schrodinger. It does preserve the mass and the energy, and we had to study sort of by hands in a sense. And then these other people, Calochen and Guardia, they study it better. So what about the irrationality? So with my postdoc, Bobby Wilson, we wonder about that. And we proved that the construction that was done in both of those results that I mentioned, so the I-team and Carl and Fau, that was done, that you could do within the resonance set to analyze your dynamics, cannot be done in the irrational one. So we are not saying that there is no growth. We are saying that the growth is going to be, well, it cannot be captured with the constructions that were done in this system. So I'm going to talk a little bit more about this. So this is after the work with Bobby Wilson, we started collaborating with Ramsky and Pan. They are actually numerical people. So we wanted to see a little bit better what was going on. So we analyzed more in details the question of the rational versus irrational torus. And let's just agree that the symbol of our Laplacian is K1 plus omega squared K2. And I'm going to call this lambda K. And when this omega squared, think of it as square root of 2, for example. It's an irrational number. And we defined the so-called quasi-resonance set. So these are the constraints that you have when you do convolutions in the frequency space. And this is the resonant part. When this is 0, it's complete resonance. And just quasi-resonant means that we have this inequality here. And this is, I'm sure that the number theorists here realize what this is for. Anyway, so this is just some definition. And one fact that I wanted to say is that when you fixed your omega, you fix your tau, and I remind you the omega is this constant here, the tau is this constant here, both positive constant, and the points that are in this quasi-resonant, but this is different 0, so non-resonant, this is a finite number of points, so you have to worry about. And the one thing that I wanted to mention is the following. You can rewrite, probably you guessed that from before, but you can rewrite the initial value problem in physical space into a Hamiltonian system with respect to the Fourier coefficients. So this is Zk, if you, in fact, more specifically, if you decompose into real part, the imaginary part, that would be the Q and the P of a typical Hamiltonian system. Anyway, so you can rewrite it like this in the frequency space. So for me, these two, I will be jumping back and forth because they mean the same thing for me. Now, a theorem that I want to mention is that if this omega is an irrational number, and we consider not the full system here, right? Not the full system here, but only, by the way, I'm sorry, there is a typo here. There should be Zk, but fortunately, I put it over here. So if I consider the nonlinear interaction that happens only over the quasi-resonant set, quartets, if you like, then this problem, so the initial value problem associated with this equation is actually well posed in L2. So if you remember before, and if you look at the whole system, then there is a loss of a derivative, the epsilon, coming from the Strichartz estimate. But if you are looking only at the nonlinear interaction in the quasi-resonant set, then you actually have Well-Posens, global Well-Posen in L2. So that was an interesting thing, and I'm going to comment a little bit on that on this. So I'm not going to write the details, but if you look at the resonance set here, and if you are in the irrational case, you will see that the resonance set means that, just like I wrote here before, you have this identity, this equals 0. At this lambda, let me do it maybe even before that. Okay, so this lambda k is this guy. This is the first component of the vector k, and this is the second component of vector k. There is an omega. So when you look at this combination with plus and minus, so k1, k2, k3, and k4, well, you see that if this is equal 0, then you will separate into the two first coordinate and the second coordinate, because the rationality of this number cannot mix things together. So what I'm trying to say here is that really by looking at the resonance set, this is not anymore a two-dimensional definition. It's actually separated into a resonant interaction in the first coordinate and a resonant interaction of the second coordinate. Now, in the first, for the 1D cubic NLS, you do have global Well-Posenness in L2, in fact, because it's 1D. So in a sense, when you have an irrational torus, you, in some cases, you can separate the problem into two one-dimensional problems themselves. And another observation is that also the 1D is integrable, and so I'm wondering if there is even something else going on here. Okay, now I want to check the time because I'm double. Sorry, I don't know what time it is, so I don't know how much I have.
It's 5:15.
Okay, good. So another 15
minutes, yes.
Okay, perfect. All right, so since we were working with people that were doing numerics, I want to show you a couple of the graphs that they were able to do. So in this first cartoon here, this is the initial data, and you see this is 0. This is exactly excitement at a low frequency. And then you let the evolution happens, and the two different pictures down here says that in the case in which you have an irrational torus, this the evolution of the way the evolution, the initial data evolves, is in within a region which is much smaller than the one for the rational case. And then in the second graph, this is even more telling. What you see here is the growth.
I must object now, because irrational and rational I get back to my fact that irrational can look rational for a long time. So this is a generic irrational on the left, I'm sure.
Yes.
Okay.
And in fact, and that's a very good point, Peter, because I asked the people who do numerics, how do you capture the rationality of something when you work with computers, right? Which is, yeah. So they explained to me that you're right, here's a generic, so you take something which looks like irrational, and everything you estimate, you do by staying within the errors that keeps that distance somehow. I don't know if that makes sense.
It'd be an irrational with a very large period. Yeah.
Exactly. So then in the second picture, you see for the same type of initial data, you see the two graphs. So the dotted one is the growth when you are in this generic rational, well, actually that's what I took, square root 2, I guess. And the other one is...
Now I'm completely happy. That is a very hard number to approximate.
Yes, you see, very good. That's what they have to do, yes. Otherwise they don't see, because they have to control the errors and they have to make less error than the error that you will make by approximating, yeah. So you see this line, it's the one for the irrational square root 2, and this one for the rational. Okay, that's just a couple of graphs. Now let me talk about the approach 2. So this, remember, approach 2, it's asking us to find an equation basically for the size of the Fourier coefficient square. Actually, for the expectation with respect to a certain probability, which here I'm hiding under the rug, really, of this Fourier coefficient square, which we're going to call nkt. So just to start, you have your solution, UTX, and now that's global. We know that it's smooth if we start smooth and so on. But we have to assume that we have a weak nonlinearity, meaning that lambda that I have put there at the beginning is going to tend to 0. And again, the zkt is the Fourier coefficient. I'm going to start with, you need probability here to do this argument. And I'm just going to say that we're going to start with initial data, which are independent random variable. There is a lot to say here about what is the density that you use at the beginning and so on, but I want to give you just very, very general pictures. And then you take some, let me write a large box limit, a weak nonlinearity limit, both limits together in a bunch of different ways. And the physicist, by take these limits in a certain sense, come up with the so-called Kolmogorov-Zakharov equation, which in general, for a general equation, we call kinetic wave equation for this nkt. So this satisfies certain equation. Now, all these limits that are done here, and if you read physics book, are, these are physics papers, so they are not, done in a mathematical sense. So there's been a lot of work recently by math physicists, especially in Germany and so on, and France, and also a group now here in the United States that have tried to make this limit process be, mathematically sound. And the first group I want to mention is Lucarin and Spawn. And what I write here in pink is exactly about what kind of distribution for the initial data you would use. And they use here at the statistical equilibrium, which means that they use the Gibbs measure, which is an invariant measure for the Schrodinger equation, or for whatever equation you're looking at. So there is no change of the density, probability density in their argument. Then there is Faou and Buckmaster, Germain, Hani, Chatin, and Deng, Hani, and Collot, Germain. They are out of a statistical equilibrium, so the density, the probability density is no longer the conservative given by the invariant measure of the system. I just want to, and usually this result have been obtained, so this limit have been proved to be mathematically, precise. But not exactly all the way to what we call the kinetic time. But there is a recent result that I was posted very recently with Deng and Hani, and they claim that they could get to the kinetic time. And now I wanted to mention another result that I have with Bintran, in which we also reached the kinetic time. So these two results were basically obtained at the same time. But while Deng and Hani was for the Schrodinger equation, we used a different kind of equation. It's called the Zakharov-Kuznetsov equation. And here is written as a stochastic equation because we allow for a stochastic piece to be here as well. This constant and this lambda, of course, are related because I'm talking about weak nonlinearity. Hence, I'm going to take lambda to go to 0, and could be also 0, this constant here. So no having the stochastic piece at all. And I want to mention that this problem was inspired by some recent work of Au. And for this equation, we want to, again, the goal is to find the kinetic wave equation of the, let's call it the Fourier coefficient of this phi here. And let me just write the theorem in a very rough terms because I don't want to introduce too much notation. But what we are doing is the following. So there is a certain density, rho, and then what you wanted to compute is this average or the expectation if you want, and we're going to call ftk. And phi hat is, again, in my notation, is the Fourier coefficient. And then we prove that if we are in the periodic case, but unfortunately we need quite a lot of dimension here to do our argument. And we start, but we have a lot of flexibility on the density we start with. It doesn't have to be either Gaussian stuff like Deng and Ani, or neither using the invariant measure that Lucarin and Spon use. It's much more general than that. And we are at the kinetic, lambda minus 2 is in fact the so-called kinetic scaling. So we are at the right scaling. And then if we take the limit of this quantity, and now what the limit? Well, it's clear lambda goes to 0. This is the weak nonlinearity. At d goes to infinity, this is just a question of we are discretizing the original equation that I give, and then you take the limit as the mesh goes to 0. The mesh is 1 over d here. And so if you take this, so this is the typical way the physicists do these limits. So if you take this limit, you in fact end up having the function f for infinity, which solves finally the so-called 3-wave kinetic equation. This is a 3-wave kinetic equation, not a 4-wave kinetic equation, which you get when you are the Schrodinger, because in our equation, we have nonlinearity, which is squared. Okay, so couple of ingredients for this.
Wait, slow down. What is this free wave kinetic equation? What does it actually mean? So what's
this actually,
I see what the left-hand side is. What's C?
Yeah, I know. So I didn't write it because it's an explicit expression that it contains.
Not linear, right?
Non-linear, absolutely. But it's explicit, and it's exactly what people expect for this type of equation here. So for each equation, you have a specific C, an operator that involves your F, and that was predicted in works on Nazarenko and so on, and that's exactly what you obtain. And it's non-linear, yeah.
It's a differential equation.
It's a differential equation, yes.
Okay.
Yes. Okay, so I just want to briefly say what it's a long, actually it's a very long proof. I want to give you just an idea of the ingredient that come in here, which are very different than the ingredient of Deng and Ani. And it goes back to the work, actually it's my collaborator who really, I was involved sort of tangentially, so it's definitely more his work because he has been educated in the world of Erdős, Yau and Spon. So it's based on some work of Erdős, some over Yau and Lucarin and Spon, and it is connected with the Feynman diagram. So in other words, the way you do this work is by using Duhamel principle to do with the iteration. And each time you do the iteration, that corresponds to a certain Feynman diagram. And then by studying these diagrams or these graphs in a certain sense, you understand what are the ones that you have to keep in order to get to the kinetic equation at the end, and which one are the ones that goes to 0 when you let lambda goes to infinity, to 0, sorry. So we do this, and of course you can do iteration all the way to infinity, but we're going to stop on a certain level m, which is going to depend on the lambda, and this lambda, when it goes to 0, this number goes to infinity, in fact, so then you capture everything. And then the game is to understand, when you start doing your estimates on each of these Feynman graphs or Feynman diagrams, what is the bound? And the bound usually looks like a lambda to the theta is positive, and lambda goes to 0, and then some function of this m lambda, but this m lambda goes to infinity. So then it's a question of balancing these two guys, and when theta is large enough, everything goes to 0, and when theta is not large enough to understand in a more granular manner to get to the kinetic equation. And at first, well, I don't want to, I don't think if I don't show you a picture, it's hard to tell, but there is a way of sorting out all these different kind of diagrams. For example, one, it's pairing and non-pairing, and then immediately you can read a bunch of stuff because you have a lot of this theta power that goes to 0. And then when you isolated this sort of pairing diagrams, you have to go more into details and using theorems from about graphs and all that stuff. And you identify what are the diagrams that really are important. These are called the ladder graphs, and these are the ones that actually give you the final equation at the end. And I'm going to stop here because I think you heard enough of what I had to say. Thank you.
Thank you very much. Questions?
In this last equation that you have with, I guess, Bintron, so you have a driving term, is that correct?
So I can.
You have, in other words, it isn't just in your initial data. You have a forcing term, which is
yes,
stochastic and so forth, and that certainly helps to make things simpler.
You're totally right, Tom. You're totally right. So that the stochastic piece, that's the one that if it is there, it helps you enormously. Right. And in fact, it gives you a lot more freedom in deciding what are the kind of distribution that you have to assume at time 0, how you distribute your initial data. And if you do have that stochastic piece, it really, the assumptions are very general. And because at the end, when you start putting inside the Duhamel operator, it really has a decay type of part in there. But if you do not have that particular forcing piece, the stochastic piece, then you are much more limited on the type of density that you can use. But we prove that we can still be off the equilibrium and neither having to use necessarily the Gaussian distribution. So
yeah, that's very helpful, of course. Yeah, that's very nice, and of course I like your result on the irrational torus. That's really kind of remarkable. So to what extent do these theorems work or apply to wave equations?
Okay. I think that in the wave equation, because of the half wave, whatever, because you have square root of, you don't have this nice different, the analytic number theoretical part in it, it's less evident. So I don't think it would be the same thing.
So what would happen? Would it be harder, easier, or what's the situation?
My feeling is will be closer to what happens in the irrational case.
So in terms of the irrational, this t to the epsilon that you have, which all you assumed is irrational, is it possible that it's bounded there?
Generic, no, I don't believe so.
For generic, now for a random in irrationality.
What's your question, Peter?
So the growth rate dropped when you periodic, it was growing,
right.
and then when it was irrational, apparently any irrational, it grew at most like t to the epsilon.
Yeah.
And so I was asking if it actually has to grow.
So
it would be very surprising if it
yes, me too. Especially if I'm thinking, so there are, and Tom knows them, the result of Bourgain of the construction. So this is for a linear Schrodinger, but with a potential, some special potential V. And he proves that there are solutions that grow to that T to the epsilon. So I will be surprised.
In a periodic or irrational?
Periodic. No, he's
you see, the irrational, there's the one thing you wrote down there.
No, you're right. That's rational. His case is rational.
I want to point out one difference between the rational and the irrational, which is all I understand about what you're talking about. That was this, what you called some result due to Gauss. I'm not sure it's due to Gauss, but it's the fact that when you write a number as a sum of two squares,
yes,
it can be written in as such in at most n to the epsilon ways with any epsilon. Yes. But if you're irrational, then it can be written in a bounded number of ways only.
Exactly, so that's what we use.
So that's the kind of thing that might reflect all the way down to what you're doing after you analyze. Yeah. But on the other hand, I understand your result. It's not so much the number of points on that curve, it's the number of points near the curve that's important.
Yes.
And that's what is why you're getting such a powerful result.
Yes.
Anyway, I agree with Tom that the irrational is very interesting there.
Yeah, it's
but maybe it's better than you think.
I was surprised of the fact. It kind of came after it was a stepping stone or something else when I realized that, for example, then the well-posedness for the resonant part in the irrational thing, it's actually an L2 global, and you can, which was kind of a surprise thing to see. And you can see, in fact, this is another interesting thing. If you look at the quasi-resonant piece, you can prove sort of conservation laws and the higher order, which reminds, because you split into the two first and second coordinates, and it's kind of like having some reminiscent of integrability in there. But this is, I had to investigate this further. It's something like that, but I don't know the extent of it.
I wanted to ask, do you have any estimate on how many points do you have besides those quasi-resonance? So you said it's finite, but it's finite and depend on probably on your initial data and your irrationality, but is there any upper bound on that?
Okay, so the quasi resonant and not resonant, I think they are close but not equal zero. So those are finite, and it depends on what is my omega, what is my tau that I put in there. So these are the constants that depend upon, but not on the initial data. It's sort of like something that depends, it's a torus, and yeah.
So do you get any results with different powers than 2?
Karen, yeah. No, I have not looked at that.
I see.
My sense is that somehow the irrational torus if you have a power which is not 2, it should be better than, should be closer to the irrational than to the rational torus. That's what I'm trying to say. Because when you solve for the resonance set, you have, if you're looking at integers in Z2, that have to be some power equals something, 0. There are not many solutions for that. So when you are not, you don't have a square or a fourth or whatever. Peter probably knows more about that.
Also, one wonders, what about toruses that aren't rectangular? There's some very special toruses that are kind of intriguing.
Yes,
there's a special torus.
It is very intriguing, and in fact, there is, and I have to think about this a little. There was a talk by Mike, what's his name? At Columbia Applied Math, Weinstein, yes. Weinstein. So yes, and he had some kind of shaped domains that are like more like a tiled in a certain way, and the boundaries are tiled in different ways, you obtain different results. I think it's something related to this in a sense. Yeah, but I didn't look into it.
Yeah,
So this is all for periodic data of various types. But once you put in quasi-periodic data, I think you don't know too much.
Ah, no. Yeah.
We don't even know the existence, even for integrable systems, except in special cases for KDV.
Yep.
I believe that's the situation.
Yeah.
So, so all this is for periodic, but once you go make your make a small variation of that, make it quasi-periodic, very nice quasi-periodic.
Yeah.
It's surprising what we don't know.
Yeah. And actually, for me it was interesting when, I was doing this just for the math, but when I worked with these two people that do numerics, they actually were interested in figuring out these differences, because they say that they are engineers actually. So when they do their experiment and they make this assumption, oh, let's do in a periodic, and then try to figure out outcomes from it that they wanted to generalize. Now, all of a sudden, they see that actually that's not, that might give you different answers depending on what you wanted to study. So for them, that was interesting, as assuming periodicity is not necessarily something that will work or will tell you the phenomenon independent of how you do that. So for them, that
you have to be able to have good control over the periods, and that's usually very hard.
Yeah, so that was their interest on this.
I assume you're aware of this actual paper that I showed Chattah and Tristan.
Yes.
That Bogan had written. They were asking me questions, and eventually,
yes, that was
something. Okay, so you know that.
Right. It is exactly for that. That's one of the papers they had, and then yes, that was.
I'm just making sure you're aware of.
Yep, that's the one. I know.
So there's another paper which is very recent. In fact, I'm looking at it right now. I was glad you mentioned the paper of Salmhofer and Yao and Erdős, because that is sort of the basic power that comes into this problem.
Yeah.
But now they have it's Yang, Yao, and Yin. They have the triple Ys. They have a new paper, and they can it doesn't pertain to Schrodinger directly, but something very close. And they can increase the time scale far beyond what they did.
Oh, that's interesting.
So it's a very serious, a very tough paper.
I can imagine.
And they only have part 1 out so far. So it's worth thinking about because they have new methods there.
Yeah, but that's always why it's interesting things. And we are trying to finish this paper. It's already 240 pages because I'm insisting. Well, I'm insisting to write, this is two communities that don't talk to each other. And I don't want you put in the thing and then I don't even understand what's going on. So this is, the math physicist writing for me. And so it's getting bigger and bigger and bigger. But
no, this is not an easy paper to read. But in fact, I still don't really understand what the key ideas are.
Yeah.
But I talked to Yao and I don't doubt that it's correct, but it's part 2 isn't even out.
Anyhow. Yeah. We'll take a look.
Yeah.
Any more questions? Well, that does not seem to be the case. Thank you, Gigliola, again for the wonderful talk.
It's a wonderful talk.
So much. Nice to see everybody, and hopefully we can see you in person soon.
Yeah.